First question is, suppose that m is a positive integer. Show that dual basis of the basis 1 till x to the m of polynomial's degree less than m is phi 0 till phi m, where phi m p is equal to j derivative of p of 0 over j factorial. Now we need to show that these are the dual basis. This is the dual basis. Recall. Let's say V is a vector space and beta is the basis, V0 to Vm, and dual basis, elements of dual basis, let us start, is equal to f1 till fn, sorry, this is n, such that fj vi is equal to 1 if I is equal to j, and 0 otherwise. 0 if I is not equal to 0. Now this is a formula. Now we need to find that what is this one. Now we can see this one is also x0. This is x to the 1 and x goes up. Now let's find our case. Now in our case our basis is right, x0, x1 up to x to the m, right? There is m plus 1 elements, and let's say dual basis is phi 0 up to phi m, such that what will happen? Phi j x to the I, since our base elements are x to the i's, is equal to 1 if I is equal to j and 0 otherwise. Now we need to find what is this phi j's. Let's take any elements in polynomial degree less than m. Let's take any p of x in PMR such that p of x is equal to a0 plus a1x till am x to the m, right? This is the general formula for elements of polynomials degree less than m. So let's look at, first let's look at the phi 0. Let's look at the general one. Also question is not the phi m. I write the question wrong. This should be right, yeah, right. This should be not the phi m, this should be phi j. For any j, phi j p is equal to p to the j 0 j factorial. Let's look at, for example, any case, first case, a0 plus a1x till am x to the m. Let's look at this one. This is equal to, these phi i's are transformations, right? Homomorphisms or linear transformations, right? So we can write this one as a0 times phi 0 of 1 plus a1 times phi 0 of x plus am times phi 0 of x to the m, right? So since we are at the phi 0, phi 0 is equal to 1, phi 0 x to the I is equal to 1 if I is equal to 1, 0 if, sorry, I is equal to 0, and 0 if I is equal to, I is not equal to 0. So this is equal to 1 and this 0, the other one also 0, phi 0 x to the m is again 0 since m is not equal to 0. So this is equal to a of 0, right? So it can go like this. If you look at this one, and this one is actually equal to, you know that this a0 is equal to phi 0 of 0, right? 0th derivative of phi of 0 over 0 factorial, since 0 factorial is equal to 1, right? So this satisfies the statement. This satisfies this one. So let's look at the general ones. Let's look at the any j. Let's look at the phi j a0 plus a1x plus am x to the m. Now, for anyone else, we have that other one 0, right? Again, that's a0 phi 0. Sorry, phi j of x to the 0 plus a1 of phi j of x to the 1 plus a j of phi j x to the j plus a m of phi m x to the, right? Now again, this is the phi j, this is phi j, sorry. There's other things here. Now again, this one is 1, right? Phi j of x to the j is 1. We know that. From here we know that phi j of x to the I is equal to 1 if I is equal to j and 0 otherwise. So this one is 0, this one is 0, this one is 0. So, and the other things also 0. We have only, what we have only here, aj, phi j, sorry, we only have aj, right? So let's look at this one. So now we need to show that this is equal to pj0 of j factorial. Let's look at the, what is pj, j derivative of ph0 over j factorial. Let's find this one. First derivative, let's look at px was a0 plus am xm, right? So first derivative will be a0 will cancel, a1 plus 2a2 plus am x to the m, right? Let's look at the jth component. J times aj times x to the j minus 1, right? So if you take one more derivative, if you take j derivative, every element till j will go, right? So these ones are all gone. So we will have j factorial times 1 plus j plus 1 till 2 times x to the j plus 1 and it goes till m times m minus j plus 1 times x to the m minus j. Right? I have this polynomial. So when we put 0 here, we will have, there is x here, there is x here, right? There. This is not xj plus 1, this is x. So there is 1x here and there is x, all the components, they will give 0. So pjx will be equal to j factor, p of 0 will be equal to, sorry, there is also j factorial times aj, aj plus 1 here, am, there is am here also. So this is equal to pj of 0 is equal to j factorial times aj. So we find that in the previously, we find that phi j of any px will be equal to aj, right? So this aj is equal to j derivative of p at 0 over j factor, right? We don't have j factorial here, so this is equal to this one. So this completes the question. Question 2 is determine all linear forms on R square which annihilate the subspace spanned by -1, 1. Now we need to find that annihilator of this space. Our subspace is U, and U will be generated by -1, 1. So this means that elements of U is of the form A minus A in R, right? Now we need to find the annihilator of this U. Annihilator of U means that we need to find elements of the dual space such that f of U is equal to 0 for any U in U. Now we need to find the elements of this space, how they are. Now take any f in U. Okay, this is also V of star, right? And elements of R square dual are of the form bx plus cy, right? Sorry. Are of the form fxy is equal to cx plus dy. Now we need to find the form of this f. Now we know that this f will be in U. So f of now take any minus a in U, okay? Now f a minus a is equal to minus ca plus dA, and since this f is in the dual space, this should be equal to 0. So this implies that ca is equal to dA for every a in U, so c is equal to d. So fxy should be of the form cx plus cy. This is equal to c times x plus y. So annihilator of U is of the form fxy's and fxy is equal to c times x plus y. So this annihilator space generated by x plus y for every c in R. Sorry, annihilator space is equal to set generated by function x plus y. Question 3 is prove that if W1 and W2 are subspace of a finite dimensional vector space V, then annihilator of W1 intersection with W2 is equal to annihilator W1 plus annihilator W2. Let's look at let's try to prove this one, and let's prove this side. and later W1 plus and later W2 is inside and later W1, W2. This is a generic algebra proof. We will take an element and we will take any elements here. Then we will say that this element belongs to this set. Then for the other side again we take any elements here and then we will show that this element belongs to this set. Then it's complete. They are equal. This is just generic algebra proof. Now take any f in and later W1 plus and later W2. So this implies that f is equal to f1 plus f2 for some f1 is in and later W1 and f2 is in and later W2. So this implies that f1 of v is equal to 0 for every w1, f1 of v1 for every v1 in w1 and f2 is equal to 0, f2 v2 is equal to 0 for every v2 in w2. These are coming from the definition of and later. So let's look at the take any v in intersection w1 intersection w2. Let's look at the f of v. F of v is equal to f of v1 plus, f1 of v plus f2 of v. Since we know that v is intersection, right? So v is in w1 but this is equal to 0. Again, v is in v2, w2. So f2 of v is equal to 0. So this is equal to 0. So this implies that f is in and later w1 intersection w2. So this completes this side. Let's look at the other side. Let's show it for the other side. And this is an exercise for you. Show that and later w1 plus w2 is equal to and later w1 intersection with and later w2. Now here we have and later v1 intersection with and later v2, right? So this is equal to and later v1 plus v2. So this is equal to dimension of and later v1 plus dimension of and later v2. And what we have here, minus dimension of and later v1 plus v2. Then we know that dimension of and later v1 is equal to dimension of v minus dimension of w1 plus dimension of this one is equal to dimension v minus dimension w2 minus this one. This one is also dimension of v minus dimension of, so there is minus here, dimension v minus dimension w1 plus w2. Now this dimension v and this dimension v cancels, so we will have dimension of v minus dimension of w1 minus dimension of w2 what we have here plus dimension of W1 plus W2. Now, dimension of W1 plus W2 is equal to, this dimension is equal to dimension of W1 plus dimension of W2 minus dimension of V1 intersection V2, right? So this W1 and this W1 cancels, this W2 and this W2 are cancelled. So we will have dimension of V minus dimension of W1 intersection W2. And this dimension is equal to dimension of n later of W1 intersection W2. So dimension of this set, dimension of n later W1 plus W2 is equal to dimension of n later W1 intersection W2. But since we know that this one is under this one and their dimension is equal, so this implies that they are equal. And later W1 plus and later W2 is equal to and later of W1 intersection with W2. So this completes the proof. Put following matrix in row echelon form. And the R matrix is 1, 2, minus 3, 3, 1, 2, and 8, 1, 9. Now we need to put this matrix to row echelon form. Let's look at. Now we have 1 here, right? This one is the leading entry. Now above this one we should have zeros. Because if Aij is equal to 0 leading 1, then Akj should be equal to 0 for k greater than 0. So for the first row, first entry is 0. So bigger i's should, for the second row and third row, the first entry should be 0. So we should add minus row 1 to row 2, minus 3 row 1 to row 2. So we will get rid of this 3. And we should also add minus 8 row 1 to row 3. Let's look at what will happen R matrix. Now after I add this one, I will have 1, 2, minus 3 here. I didn't do anything for row 1. Then I will have 0 here. Then I will have minus 3 times this one is minus 6 plus 1 minus 5. Then I will have 9. 9 plus 2 is 11. I will have this one. Now let's look at this one. I have minus 8 times 0. Minus 8 times 2 is minus 16 plus 1 minus 15. Minus 3 times 8 is 24 plus 24 plus 9 should be equal to 24 plus 9 is 32. So I need to make this one is also 1. So I will have 1, 2, minus 3. I divide row 1 to minus 5. So I will have 0, 1, minus 11 over 5, 0, minus 50, 32. Here, for the row 2, I have 1 here. So I don't want this 15 here. So I should subtract 15 of row 2 from here. So I will have 50 row 2 to row 3. Then I will have 1, 2, minus 3, 0, 1. That's 11 over 5, 0, 0. Minus 15 times this one is sorry, I add plus 15 row 2 to row 3. Then I will have here minus 13 plus 13. This should be 0. And this is the row echelon form. Let's look at whether this matrix satisfies the condition or not. Any row only zeros of A is at the end, right? There's only this row which contains only zeros and it's at the end. For a non-zero row of A is leftmost non-zero. For any non-zero leftmost non-zero entry should be 0, right? This row is non-zero and first non-zero entry is at leftmost, and also like this one, this row is non-zero and leftmost entry is the first non-zero entry. Now, and this last one, now third one is if Aij, let's look at, for example, this is equal to 1, is the leading one, like this is the first entry of this row and it's 1, and the other column they don't have this one. Below columns don't have 1, don't have any non-zero entry. Here this one is the leading one and the above this one there is no 0, and these are two leading ones, and for example this one is less than this one and J's column is column number also less than this one. So these are satisfies the condition for row echelon form. So this is the row echelon form of this matrix. Question 5. Find the solution set of the system Ax is equal to 0 over the field of complex numbers where A is the matrix of 1 minus 1 plus I 0, 1 minus 2 1, 1 2I minus 1. Sorry, this one is I. This one is I. This is the R matrix, right? Yeah. This is our matrix. Now, our augmented matrix for this system is equal to I minus 1 plus I 0, 1 minus 2, 1, and 1, 2I minus 1, 0, 0, 0. Now, we need to solve this augmented matrix. Now, let's solve this one. Now, we need to put this matrix, to find the solution easily, we need to put this matrix into row echelon form. So, there is I here, right? So, I want to get rid of this I, so, and make that one to 1. So, I will make minus I times row 1. So, I will have minus I square. Minus 1 times minus is 1. Minus I times minus 1 is I. Minus I times minus I is minus 1. 0, 0. And I did nothing for the other rows. Okay, this one is the leading entry. So below this one, we should have 0. So we need to cancel this one and this one. So I can add minus row 1 to row 2, then I will get rid of this one, and again minus, again minus row 1 to row 3, right? So I will have I will have this matrix will become this one will become 1 I minus 1 0 0. The first row does not change, so I will have here 0, and here I will have minus of this one. I'm adding minus plus 2 minus 1 I minus 1 again here. Then here I will have 1 here. There, since there is 0 above it, there is nothing. Again, I have 0 here. 2i minus I minus 1. 2i minus I is I. Minus minus I plus 1. And I will have here minus 1 0. Okay, this is the what I have. Did I make correctly? I plus 1. Is it right? Yes. This one is minus 1 minus I. Sorry, this one is minus I minus 1. Okay. So if you see that, this one is minus of this row, right? Minus row 2 is equal to row 3. So I can add row 2 to row 3. So I will have 1 I minus 1, 0 here. So then I will have 0, minus I minus 1, 1, 0, 0, 0, 0, 0. So there is 2 non-zero, right? But there is 3 unknowns. So this system has infinitely many solutions, because number of unknowns or variables greater than number of non-zero rows. But we need to find this infinitely many set. Now since I want to make this set is row echelon form, I want this one 1. So I can multiply this one by minus 1 plus I over 2. Then I will have row 2, 1 I minus 1, 0. This is the complex conjugate. Then I will have 1 square plus I square 1. 1 plus 1, 2. Norm of this one is 2, 0. 2 over 2 is 1. Then minus 1 plus I over 2, 0, 0, 0, 0, 0. So now we need to find this set. What is this set? Let's say z is equal to t, right? There is 1 in the column for x and there is 1 for the column for y. So let's say z is equal to t. Then y is equal to, let's look at the second row. We can see that y is equal to y, second row gives us y plus minus I over 2z is equal to 0. So y is equal to 1 minus I over 2 t. So this is the 2 is everywhere. So this is the y, and let's for the first row gives us x plus I minus 1y is equal to 0. So x is equal to 1 minus I times y. And we know that y is equal to 1 minus I times 1 minus I over 2t. Let's look at the 1 minus I. 1 minus I is equal to, is it 1 minus I? 1 minus I and this one will be equal to 1 minus I square should be equal to 2I minus 2I over IT. This is equal to minus IT. So the solution set will be equal to x will be it, y will be 1 minus I over 2t, and z will be equal to t, and t is arbitrary. T is any element in R. So this is the solution set. This is the solution of the system. Question 6 is find all solutions of the following Clenary system. First one is this one. A, x1 plus x2 minus x3 minus x4 is equal to 0. x1 plus x3 minus x4 is equal to minus 1. 2x1 plus 2x2 plus x3 minus x4 is equal to 2. Augmented matrix for this one. Let's write augmented matrix of this system will be, here we have 1, 1, minus 1, minus 1, and the solution is 0. And here we have 1, there is no x2, so we have 0. There is x3, there is 1, there is minus x4, so we have minus 1, 0. In the third row, we will have 2, 2, 1, 2, 2, 1, minus 3, 2. Sorry, this one is minus 1. The solution is minus 1. Now we need to solve this augmented matrix. Let's try to solve this one. I want to write this one also in this page again. So I have 1, 1, minus 1, minus 1, 0, 1, 0, 1, minus 1, minus 1, and 2, 2, 1, minus 3, 2. So let's try to solve this system. So here I have 1, this leading one here, right? So I want to make this one and this one 0. So below should be 0. Then I should add minus row 1 to row 2. And I should add minus row 1, minus 2 row 1 to row 3. So then I will have here, what I will have. This is the same 1, minus 1, 1, minus 1, minus 1, 0. Here I have minus 1, plus 1, 0, minus 1 times minus 1 plus 1. Here I have 2 plus 1 minus 1, 0. There is nothing here, so this should remain the same. Let's look at this one. Minus 2 plus 2, 0. Minus 2 plus 2, 0. Minus 2 times minus 1 is 2. 2 plus 1 is 3. Then I will have minus 2 times, minus 2 times this one is 2, minus 1 is equal to 2. So let's make this one into row echelon form. Leading entries should be 1, 1, 1, minus 1, 0. So let's make minus row 2 and row 3 over 3. Then I will have 1, 0, 1, minus 2, 0, 1, 0, 0, 1, minus 1 over 3, 2 over 3. Let's try to solve this system. Let's say x1, x2, x3, x4 is equal to t. Then from third row, we have that x3 minus x4 over 3 is equal to 2 over 3. So x3 will be equal to 2 over 3 plus x4 over 3. So x3 is equal to 2 over 3 plus t over 3. Let's look at the second row. From second row gives us x2 minus 2x3 is equal to 1. So x2 is equal to 1 plus 2x3. So this is equal to 1 plus 2 times 2 over 3 plus t over 3. Then I will have 4 over 3 plus 1 is equal to 7 over 3 plus 2t over 3. Let's look at the first row. Gives us x1 plus x2 minus x3 minus x4 is equal to 0. So then I will have x1 is equal to minus 60, x2 plus x3 plus x4. This is equal to minus 7 over 3 minus 2t over 3 and plus 2 over 3 plus t over 3 plus t is equal to this one will gives us 7 over 3 plus 2 over 3 will gives us minus 5 over 3 minus t over 3 plus 2t over 3. So this is equal to x1. So solution set will be equal to minus 5 over 3 minus 7 over 3 2 over 3 0 plus t times 2t over 3 and 2t over 3 t over 3, sorry, I write t here, t times 2 over 3, 2 over 3, 1 over 3 and 1 and t is enough. This is the solution set of the system. System of the part B is x1 plus x2 plus 2x3 is equal to 4. x1 minus x2 minus x3 is equal to minus 1. 2x1 minus 4x2 minus 5x3 is equal to 1. Let's write augmented matrix first. Will be 1, 1, 2, 4, 1 minus 1 minus 1 minus 1, 2 minus 4 minus 5, 1. Let's solve this one. Let's make this matrix into row echelon form. Now, I want to cancel this one and this one. So I add minus row 1 to row 2 and I add minus 2 row 1 to row 3. So I will have 1, 1, 2, 4. Row 1 will stay the same. Now I will have here 0, minus 1, minus 1, minus 2, minus 2, minus 1, minus 3, minus 4, minus 1, 5. Then here I will have 0, minus 2, minus 4, minus 6, minus 2 times 2 is minus 4, minus 9, minus 4, minus 8, minus 7. Minus 8 plus 1 is minus 7. So again, I can cancel this one. Sorry, I can cancel this one with this one, right? So I add 3 minus 3 row 2 to row 3. So I will get 1, 1, 2. I will change this one. 0, minus 3, minus 5. So minus 3 times minus 2 is 6. 6 minus 6 is 0. Minus 3 times this one is plus 9. This one is 0. Minus 3 times minus 5 is 15. 15 plus minus 7 is 8. But here we have a bad row, right? If I look at this one, this row means that 0 times x1 plus 0 times x2 plus 0 times x3 is equal to 8. So this means that 0 is equal to 8, but this is not the case. So system is inconsistent. So the system has no solution. Since we have a bad row here, we don't have any solution because 0 is never equal to 8. Question 7. Question 7. Find the values of a for which the system 2x minus y plus 2az plus t is equal to b, minus 2x plus ay minus 3z is equal to 4, 2x minus y, 2a plus 1z, a plus 1t is equal to 0, and minus 2x plus y, 1 minus 2az, z minus 2t is equal to minus 2b. Minus 2 over r has unique solution, infinity many solution, and no solution. We need to find these cases. Now let's first write the augmented matrix of this system. Okay, augmented matrix of this system should be, we have 2 minus 1, 2a, 1, b in the side. Then we have 2a minus 3z, and there is no t, so this should be 0. And we will have 4 here. Here we have 2 minus 1, 2a plus 1, a plus 1, 0. And we will have minus 2x, so minus 2 plus 1, 1 minus 2a, and minus 2 is equal to minus 2b minus 2. So this is our augmented matrix. Let's try to make this matrix more usable way. More usable. Okay. Now, let's try to make this one more like row echelon form. This should be leading entry, right? There's 2 here. So I want to cancel all these ones. I want to cancel all these ones below 2. Then I should add plus row 2 to row 1 to row 2, minus row 1 to row 3, and row 1 to row 4. Then I will have here 2 minus 1, 2a, 1. I didn't do anything for the row 1. Then I will have a minus 0, a minus 1, 2a minus 3, 1, 4 plus b. Then I will have, here I will have 0, 0, 2a plus 1 minus 2a is 1, a plus 1 minus 1 is a, 0 minus 1 b. Here I will have 0 and 0, 1 minus 2a plus 2a, 1, minus 2 plus 1 is minus 1, and I will have here minus b minus 2. Now, this is the leading entries, there is nothing here. This is the leading one, there is nothing here. Let's say this is the leading one, there should be nothing here, so I will add minus row 3 to row 4. Then I will have 2 minus 1, 2a, 1. I didn't do anything for this row. 0, a minus 1, 2a minus 1, 1, 4 plus b, 0, 0, 1a minus b, 0, 0, and 0, a, 1 minus a, and b minus 2 minus b is minus 2. Now, first thing was to show this system has a unique solution. To have a unique solution, this system should have rank 4. Okay, so this system should be 4 non-zero rows. So since there is this one and this one, first entries are non-zero. To have this system rank 4, this one and this one should be non-zero. So there will be 4 non-zero rows. So for part A, system has unique solution. If and only if this one, a minus 1, not equal to 0, and this should be together, and minus 1 minus a should be non-zero. So a should be not equal to plus and minus 1. If a is not equal to plus or minus 1, then system has a unique solution. Let's look at the part B. Before part B, let's look at the part C, where the system has no solutions. So, we should have bad rows, right? We should have inconsistency between rows. Like, this is obvious, right? If this row gives us 0 is equal to minus 2, then there will be no solution. So if 1 minus a is equal to 0, then system gives us 0 is equal to minus 2, right? So there is no solution. So a should be equal to 1 if and only if a is equal to minus 1, then there is no solution. So let's look at, is there other possibilities. Let's say we make this one is equal to 0. Let's make this one also equal to 0. Let's look at the a is equal to 1. What happens if a is equal to 1? If a is equal to 1, the system becomes 2 minus 1. This part becomes 2, 1, b, 0, 0, 2a minus 3, and look at here, 2a minus 3 will give us minus 1, 1, 4 plus b, 0, 0, 1, 1, minus b, 0, 0, 0, minus 2, minus 2. So here let's look at this system. Well, let's add row 2 to row 3. Let's add row 2 to row 3. Then I will have 2 minus 1, 2, 1, b, 0, 0, minus 1, 1, 4 plus b, 0, 0, 0, 2, 4 plus 4, 0, 0, 0, minus 2, minus 3. So after that I can cancel also this one. Then I should make minus, sorry, not minus, row 3 to row 4. I should add row 3 to row 4. So I will have 2 minus 1, 2, 1, b, 0, 0, minus 1, 1, 4 plus b, 0, 0, 0, 2, 4, and I will have 0, 0, 0, 2. Again, there is a bad row, right? So this gives us 0 is equal to 2, right? So there is no solution. Because 0 is not equal to 2. So if for part C, if a is equal to 1 or a is equal to minus 1, then the system has no solution. Now for part B, we need to find where the system has infinitely many solutions, right? Now, in part A, we show that if a is equal to 1, if a is not equal to 1, and if a is not equal to minus 1, then system has unique solution. And part C, we show that if a is equal to 1 or a is equal to minus 1, then system has no solution. So, these three, part A and part C, we see that for a is not equal to 1 and a is not equal to minus 1, system has unique solution. For a is equal to 1 or a is equal to minus 1, system has no solution. There is no remaining case. Okay, so there is no, for no value of a, the system has infinitely many solutions. So this was the end of today's problem solving session. See you next time.